Hello, and welcome back to Data-Driven Methods in Dynamical Systems. So today I want to talk to you about this watch. Is this guy right here, the Casio F91W. Let's see if we can get a focus on it. Boop. There we go. So this is a cheap watch. It is super cheap. It is like 15 bucks, and I just bought 4 of them for each member of my family because I'm a watch collector, and so my 2 toddlers had just turned 3 years old, and they got their first watch. It was identical to this one, just slightly different colorways. Like I said, I'm really into watches, and one thing I've always really kind of wanted to know is why are quartz watches so accurate? This Casio F91W is more accurate than a $10,000 Rolex. And yeah, so the question is, why? Now, it can be traced back to 1600s with Christian Huygens, who introduced the pendulum clock. He heard from Galileo that there was this sort of isochronometric property of pendulums, period. So basically, no matter how big the swing of the pendulum, it always sort of takes the same period to go from one way to the other. The only things that really influence the length of time it takes the pendulum to go from one side to the other is the weight of the object at the bottom and the length of the pendulum. And so as long as these two things stay together, you will get an accurate description of the time just by watching a pendulum. So then basically what you can do is you hook up this pendulum to what is called the mainspring, which is like the main power source of a mechanical watch or a clock. And basically you put a little trigger on the end of your pendulum. This is called an escapement, where each swing of the pendulum lets the mainspring unwind a little bit more at a time. If the escapement wasn't there, then the mainspring would just fly like crazy, and you would watch the time run into the future as if you're in the movie Time Machine. Now this is a pendulum escapement, and this was used for clocks. Now if you look at a watch, a mechanical watch, this is a really cheapo fossil mechanical watch. So it has a display case back, and there's and they let you see what is called the balance wheel right here on the front. And so if I get it focused just right, yeah, you see that little guy beating along? That is the heart of your watch, and that is a pendulum. It is a round pendulum, and is basically a circular bit of metal which has a spring on the inside. The spring is called a hairpin, and the length of that spring really determines the period of the pendulum. And if you look at the very back of this guy, here, let's get zoomed in again. There is a tiny little lever that you can pull there, and that'll lengthen or shorten your spring. There we go. And so a watchmaker, if they're trying to tune a watch and make it more accurate, they will lengthen or shorten that spring in order to tune the accuracy. You can do this up to a couple seconds in a day. And so, and that's how watches are regulated. There are a lot of issues that come up with balance wheel escapements, and a lot of things that can affect the accuracy. Things like temperature and magnetism, and a lot of these things have been, with better and better materials, better material science, we've been able to get rid of a lot of those issues. There's also positional issues. If you put the watch on one side, maybe crown down or crown up, it'll actually change the accuracy of the watch that way too. And so one way that people actually try to get around that one is they invented what's called a tourbillon, a cage that goes around the balance wheel and sort of rotates it as it goes along. Now this was a lot more effective in, say, a pocket watch which held one position at all times, rather than a wristwatch, which is going to, the orientation changes throughout the day for a wristwatch. There's all sorts of different ways that people have invented through, say, from the 1600s to the 1800s, even into the 21st century. People are coming up with new ways of improving the accuracy of timepieces. After a certain point, mechanical watches really fall short of the capable accuracy of a wristwatch. And this comes down to technology that was developed mostly in the 20th century. In the late 1800s, we started realizing that quartz actually had what is called a piezoelectric effect. So if you hit it with a hammer, it actually let out an electric charge. But conversely, if you put an electric charge into a quartz crystal, you can actually get some movement out of it. And the amount of movement and the amount of vibrations you get by throwing electric current through a quartz crystal changes depending on the shape of the crystal. And so with a little tuning fork shape, we can actually make exactly the frequency we want to come out of it. Now, the reason why we choose that particular number, 32,768, is that it's a power of 2, and it's 2 to the 15. This frequency is high enough that we won't be able to hear it with human hearing, but it does fall within the threshold of your dog's hearing. And it is still a low enough frequency that a cheap counter can keep track of how many times a vibration has occurred. Once you hit, so basically a counter is just flipping a whole bunch of bits, and if you have 15 bits that a counter is using, then it'll go from 1 to 10 to 11 to 100, etc., until it fills everything up with ones, and then adds one more and it flips to 0, and this is called an overflow. Once you overflow, it tells a Quartz computer that we should advance the seconds by 1. And so, and this is how a Quartz watch works. So turns out Quartz watches are very cheap to make. The first Quartz watch that went into regular production for consumers was the Seiko Astron. And the Seiko Astron was introduced in 1969, and it hobbled the watch industry. Basically, everybody who was making mechanical watches had trouble selling them because, you can make a Quartz watch by the 80s for like, $20, and this one, for $15 by the time you got into the 90s. So that really made people just not want to buy super expensive watches, and they would, unless they were a watch collector. And then the consumers spoke, and they went after Quartz watches. A lot of these watch companies that used to be like paragons of watchmaking, like Hamilton and Tissot and many others, ended up going bankrupt and getting bought out by major watch conglomerates. So all of these are now owned by Swatch, and Swatch also owns Omega, which is a big competitor for Rolex. The question is, how do you determine how accurate a watch is? It's not like we're going to sit down and look at a watch and just count the seconds ourselves. So if we're using another watch to time another watch, what I'm going to do is I'm going to take this watch and this watch, and their vibrations per second corresponds to this balance wheel. This balance wheel should be going at about 6 hertz, or at least it should induce 6 hertz, 6 vibrations per second. This is a sort of a cheap Miyota movement. I think the Miyota movement itself is about $20. This is a little bit more expensive, and so this is a Seiko Alpinist, and the movement inside there, is a little bit more sophisticated than the Miyota, although they both run at 6 hertz. And so what I'm going to do is I'm going to take these watches and I'm going to put them up to my microphone that I usually use for recording lectures, and I'm going to crank up the gain. The gain on the microphone, once it's cranked up, will be able to detect the little vibrations coming in from the balance wheel, and then we can find the frequency component of that audio signal's Fourier transform. And so now that leads me to what I want to talk to you about on the mathematical side, and that is the Fourier transform. So I want to talk to you real quick about what the Fourier transform is. So the Fourier transform is basically a transformation from the time domain to the frequency domain, where basically the time domain information is what you would hear if you played an MP3. It's the things that you hear through time. But then we transfer it to something called the frequency domain through what is called the Fourier transform. And this will emphasize different sorts of periodic behaviors in your signal. And so in this case, if you just have a regular sinusoid of 1 hertz, then when you take the Fourier transform of that sinusoid, you should have a peak right at the 1 hertz point. And that's basically what the Fourier transform does. It basically tries to reassemble all your information of your signal and decompose it into a whole bunch of sinusoids. So ranging from, say, 1 hertz, 2 hertz, 3 hertz, up to thousands of hertz, depending on the signal itself. And so the way it does it is basically, let's say we have a function defined over a finite interval, 0 to 5 seconds. And what we're going to do is we're going to take the integral from 0 to 5 of f of x times e to the minus I 2 pi kx dx. And in this case, k would be our frequency. Now, that will end up extracting the frequency information at the kth frequency. And as you change k, you go through and you march through your different frequency bands. If we were able to perform an exact integral, then this would work out fine. But the thing is, we only have samples of our function. And so what we need to do is we need to change this from being a full integral to a sums or basically through some sort of Riemann sum of the integrand. And so what you get in that case then is you get a discrete collection of points, and we can even remove knowledge about the time, and we'll just use just the outputs and do a Fourier transform on that. And then at the end we can transform the frequency domain, pulling back in something like our sampling rate, and then we can readjust the frequency there, but overall it won't really matter as far as the actual shape of the graph. Everything will just end up being rescaled in the frequency. So basically what we're going to do is we're going to assume that we have samples, say f0 to f1 to f2 all the way up to fn, where n is the total number of samples that we have. And what you do if you want to take the discrete Fourier transform of the sequence of points, what you're going to get is you're going to get, say, fk hat. And fk hat is equal to the sum from j equals 0 up to n of f sub j times e to the minus I 2 pi j times k divided by n. This is the discrete Fourier transform. Now, if you want to get your data back from the Fourier transform function, so we have, so now we have a new sequence of points that come from our Fourier transform, and this represents our frequency content. And so these are all at f0 hat, f1 hat, f2 hat, all the way up to fn hat. You can do what is called an inverse discrete Fourier transform, where you recover fj from the sum of k going from 0 up to n of fk hat times e to the I 2 pi jk divided by n, and then you divide all of that by n itself. And what this ends up giving you is a sort of forward and backwards transformation where you can go to the frequency domain and then you can recover your signal there. You can do all sorts of cool things in the frequency domain, and we'll look at some of the things that we can do here, where you can basically do filtering, where you can allow some frequencies through and kill other ones, and then bring your signal back to the time domain, and you can, say, eliminate noise or isolate a very particular frequency. This would be a bandpass filter. So one thing you can note is that if you take a look at all the components inside of the discrete Fourier transform, or even the inverse Fourier transform, you basically have one critical frequency value, one critical complex number that you're just exponentiating. This is going to be e to the minus I 2 pi over n. And this quantity itself is being raised to the j times k throughout your sums. And so what you can do, if you've seen my van der Waals interpolation video, you can use the same reasoning in order to make a linear system out of the discrete Fourier transform, and it'll give you a matrix that you can just invert to get the Fourier transform itself. So that way you don't have to do it one by one each time, and MATLAB works a lot faster doing matrix manipulations than it does, say, doing for loops. So what you could do then is you say take a look at k being 0, and so you're looking at f0 hat. And this is just going to be a sum from, say, j goes from 0 to n of f sub j times that special quantity, let's call it omega, raised to the 0th power. So that means it's just basically a sum of f1 plus f2 plus all the way up to fn. And so then this can be rewritten as a column vector of just ones times the vector that we get from our samples of f1 down to fn. So then you can make that into your first row of a matrix, and then you can take a look at the next matrix, where you choose k being 1. So you're looking at f sub 1 hat, and this will end up being the sum j equals 0 up to n of f sub j times omega raised to the j times 1. Then you can spool this out into a row vector of 1, and then omega squared, and then omega cubed up to omega n. And this times, again, our data points, f0 down to fn. And then you can continue this until you get all the way up to k equals n. And so you have f sub n hat is equal to the sum of j going from 0 up to n of f sub j times omega raised to the j times n. And so what this turns into becomes 1 omega n omega 2n, omega 3n, all the way up to omega nn. And so then, therefore, you have completed a full matrix times your data values, and this is all equal to your discrete Fourier transformed values on the other side. And so this matrix is certainly invertible, and then you can perform your entire discrete Fourier transform by multiplying this matrix times f sub j, and then you can invert it by multiplying the other side by the inverse. Unfortunately, though, the matrix inversion is at least big O of n squared, if not big O n squared plus a little. And that's really computationally expensive, especially when you get to have a large number of points. And so what we're going to be dealing with here is going to be, we're going to have 48,000 samples per second. And so that is way too high to be doing anything computationally that should be on the order of big O of n squared. You're going to choke everything really, really fast. So then Cooley and Tukey, they released a manuscript back in I think it was the 1970s. I'll find the paper here. And in that case, in that setting, they found a really efficient algorithm, and this is called the fast Fourier transform. The fast Fourier transform basically splits up the data into powers of 2 and then finds clever ways of recombining it. And what this ends up giving you is it gives you a computational complexity of big O of n log n. Now, you can never beat the big O of n in any sort of data context, because you have to at least read your data at some point. So having an algorithm that's big O of n log n is really the next best thing that you could possibly have. This is on par with what is called merge sort, if you know what that is. Anyway, so the FFT is what you should actually be using rather than this matrix inversion approach. And in this case, we're going to go ahead and use MATLAB's version of the FFT, and which gives you something a little bit awkward. So we're going to use also MATLAB's FFT shift command to put everything, to zero everything out. So here I'm going to go and real quick show you how you can figure out how accurate a watch is, or at least what the frequency you're looking at is. Let's go ahead and jump into some MATLAB. Okay, so we're here set up with MATLAB right now. Last night I waited until it was quiet in my house because it's hard to find quiet time, and I took my Alpinist and I recorded the sound coming out of it. I don't know if you can hear much coming out here, but if you put it up to this microphone and you turn up the gain and you find exactly the sweet spot where the audio is coming from, or where it detects the audio, you can pick up a fairly decent signal. It's not stellar. Let me see if I can go ahead and find it for you. Oh, here. Let's play this. So this is a segment I put in MATLAB, and so I don't know how well that's translating. Maybe I'll dub over this and put the actual signal up. But yeah, you can kind of make out the ticking of the balance wheel, but unfortunately, it's they're surrounded by a tremendous amount of noise, which really makes the signal hard to pick out. So let's go ahead and take a look and see what I set up here. First of all, I put everything into what I call Alpinist long record. So I recorded for something like 2 minutes, something like that. I ultimately didn't use all that data, but I wanted to have as much data available to me as I could. And so the sampling rate comes out here out of audio read, and in data, it just dumps the actual raw data. This is all the output. So like I was saying with the Fourier transform, the Fourier transform itself, the discrete Fourier transform itself doesn't really care about the time or the frequency. It just cares about the outputs and tries to recombine them into what it calls the discrete Fourier transform. And it's up to you to later go on and interpret exactly what the frequency means. And that's what you use FS for. Which is the sampling rate, and here it should be 48,000, which corresponds to this microphone in particular. So what we did then is, so I went in and I just made sure it was an even multiple of 48,000 just to make things easy. So it looks like I was just short another second here, but I chopped it off after doing a mod on the length of the data to figure out exactly how much to take out. And I'm only using the second channel here. So this is a stereo microphone, so it gives me left and right channels. And here it gives me, so I just select one. Then after that, I segmented my data. using the reshape command. So the reshape command takes, like, say, a long vector or a different matrix, and then it chops it into segments, and then it restacks it how you want. And so here I told it to take 48,000 of our elements and then multiply that times 5. Now remember, our sampling rate is 48,000 hertz, so that means that this is 1 second. Each one of these is 1 second, and so 5 of them is 5 seconds. And I didn't know how many should end up being as far as my my columns go, but ultimately it'll decide itself if you put this in empty brackets in there. All right, so I tried to do some mean subtraction. That didn't work, so let's get rid of that. And so we'll just go ahead and jump into the FFT. So I took the FFT of the audio signal, and it gave me this. So I'm going to push play, and I'll show you some of the things we got. That's my cleaned up signal here. Didn't mean to play that. So here's the original signal. Kind of funky, and it you can't really pick out much there. There should be some sort of regularity to the signal because there's the balance wheel, but it's still surrounded by a lot of noise. These peaks here probably correspond to the balance wheel, but I'm not entirely sure. And so if you take a look at the FFT of the signal itself, the frequencies here it goes up to are fairly high, and it looks like we're still getting a lot of high frequency content. And usually I would just sort of get rid of that, but it turned out that it was actually important. So if I take a look in here, we have a ton of low frequency noise, just like huge mounds, and the alpinist runs at 6 hertz. And so I went down and tried to see if I can see anything at the 6 hertz. And there really wasn't much going on here. You could see some sort of mound showing up around maybe the 12 hertz, and that could be a harmonic. But around 6 here, there's not much. And then compared to the amplitude on everything else, I mean, that is just tremendous. And so what I started doing is I started using a bandpass filter. So where I declare that all of this content should be 0, and maybe all of this content should be 0. And I moved this little wave all the way around until I found something. And the first place I found something was here. So it turns out that this bit is actually everything about the balance wheel's noise. And so then I later made a sort of a trapezoid rule, sort of a trapezoid, not trapezoid rule, but I made a trapezoid here around this. And so I had a sort of an increase on my bandpass, and it was level out, and then a steady decrease. It's still not the greatest kind. You usually want smooth bandpass filters because otherwise you're going to introduce some Gibbs ringing, but yeah, this is just a toy example anyway. And so after I did that, well, let's see, let's just go ahead and see what it looked like in the code. So I'll move these over here. And so here we go. So first I did the FFT, and then the FFT shift makes sure that the 0 frequency is actually right in the middle. Then after that, I need to figure out exactly what the frequencies were. So I took the length of the sample, the total number of samples, and also the frequency of my samples. I took their quotient, and then that gives me sort of my frequency bins. And so then after that, I just take a vector of length L, and I split this between sort of minus L over 2 and L over 2, off by 1, so I took off the last bit, and this became ultimately all of my frequencies. And so then this plots the FFT signal that we just saw. And here comes the bandpass filter. So this is really just a linear thing, but a piecewise linear problem. You can make it do some sort of clever stuff. So basically, this is so I take each one of these matrix elements and I pointwise multiply them. So that's what the point star is, and then by this, and this is our piecewise Heaviside function. And so this is more or less going to be so basically this rises up. My slope here is positive if you take a look at this, and my second slope is going to be negative. So basically it's going to be 0 for a while, and then it shoots up to 1, and then it goes on and then I have another one that I multiply the opposite direction. So it's 1, 1, 1, and then it drops down to 0, and it translates and interpolates the 1 and 0 point linearly. And exactly where it starts the interpolation is here, going from 0 at 9900 to 1 at 10,000, and then it starts from 1 and it goes back down to 0 from 11,000 to 11.5 thousand. And and so that's basically all that is. And so this is implementing a bandpass filter, and then after that we just want to get our data back. And so basically what we have is we have our audio matrix here, the FFT of that huge matrix that we made through reshape, and I have it plotting the mean over all of our FFTs, sort of just get what happened. But yeah, we don't really need to do that anymore. Let me just show you what the raw is. So there we go. The mean can help clean up some noise if you have a lot of samples and etc. and it's more or less the same sort of content, and then you take the frequency transform and you take the average, then you should get something. And so instead we can just go ahead and change that from the mean. But if you just want to see what that looked like, so basically what we did here is we took the Fourier transform, and then I did a band pass filter. So I zeroed out everything except for this little region, and 0 outside of there. And so that killed all of this stuff in the middle. It killed all the stuff that is higher and just left this little bit. And if I moved it too far to left or right of that region, then you end up losing the signal altogether. So that told me that this was the right frequency range. So then what we do? After that, what we want to recover the original function. So basically I did an FFT shift to the audio matrix, so I need to undo that, so it's IFFT shift. And then after that I want to do the inverse Fourier transform. We already defined what that was. Now we're going to pick up some complex numbers here, and we don't want those, so I'm just going to slip a real in here to sort of zero out all the complex numbers. And then once we do that, we can use this information and in the sound function to give it a shot. And then I need to figure out for the plot what my time domain is again, and so basically that gives me that. And so this gives me my filtered audio signal, and so this was the original audio signal, and the filtered one is right here. And so, oops, did I mean to click that? There we go. And there we go. And so now we can actually see these peaks. So this came from the balance wheel sound that you heard before. And so this, you can actually count the number of peaks here, and that'll give you an idea. And so what you can see is that this peak here and peak here, there's 30 peaks altogether. And basically we can take the difference between the x values, and basically we can say 30 divided by that, it should give us the right answer that we want. And if you do that, then what you end up getting is 6.205. Now it says 6.2 and we're dividing by basically 5 in here. And so I'm wondering if maybe my count was off a little bit. Maybe I should have just done 6, counted the 29 of them, and then divided by that, and then that would give me pretty much 6 on the dot. The reason why I say that is because if it was 6.2 rather than closer to the 6, then what I would end up having is I would have a huge drift in seconds per day. That would make me lose hours. I'm certainly not losing hours on this watch. So sort of off by 1 error. And so if I take 29 divided by this, oops, then it's 5.998. So it tells me that my watch is running just slightly slow, and that seems a lot more reasonable. Anyway, so that gives you a quick idea of how you can do sort of a watch timer time grapher on using MATLAB. Now it was sort of interesting that we didn't see so much of in here. Let me go ahead and play the audio signal for you again. So this is a cleaned up signal, as opposed to the one that wasn't cleaned up, which is this guy. And so you really can't make out that second one, make out the balance field very well as the second one. And so it's remarkable how much you can really, using just some bandpass filters and some really quick things that you can do in MATLAB in a few minutes, and recover such a strong signal coming out of the middle. Now I find it interesting that that it didn't end up giving me a 6 hertz frequency in the spectral decomposition, and that was alarming, and I scratched my head for a long time. I consulted with my wife. She sent me some FFT code that was all commented in German, and I think it might be her telling me to get off my butt and learn some German. But yeah, the interesting thing was that I just didn't see the 6 hertz signal, and so I went through and I did my best at evaluating exactly what I was doing here. And so just as a sanity check, I did the whole code all over again, but just with a single sine that has a 1 hertz frequency. And when I ran it, well, I got that my sine. I got the sine back perfectly when I did the inverse. And here, you can see that I have a pulse right there at the 1 hertz signal. And so that tells me that at least in some respect, I'm not crazy. So if you know why I wasn't seeing a 6 hertz signal coming out, yeah, I'd really appreciate it. Especially when you can count the 6 hertz right there with your eyeballs after I filtered everything out. But I figure everything but just must be falling into the harmonics, and that's what we're really picking up there. Anyway, so thank you for watching, and yeah, that's how you make a time grapher. All right, so if you like this, go ahead and subscribe, and if you didn't, yeah, subscribe anyway. I wouldn't mind. All right, so I'll see you next time.